to another video with Mohammed and I. Today we're going to talk about port channels and a guide to link aggregations in modern networks. Mohammed, how you been? It's been a while since we made one of this.
I'm doing good. Let's run some port channels.
All right, let's get into some port channels. So what is a port channel? A port channel, often referred to as a lag or an ether channel, is a logical interface made of two or more physical links. Some of the key technical properties of it are that it increases total aggregated bandwidth, it provides per link redundancy, it appears as a single spanning tree or routing interface, depending if you're doing some layer 3 port channels, which we can get into. Avoids blocked links from spanning tree, supports load balancing hash algorithms, and some of the technical requirements are all physical members must match speed and duplex, trunk and access modes, VLANs, MTU, and spanning tree settings. Both ends must negotiate or be manually configured. So let's talk about what this slide means. We'll get more in depth further, but essentially, as we've learned in our previous videos with spanning tree, when you connect multiple interfaces, one is going to become blocked. What port channel is doing is actually aggregating both of those interfaces and creating redundancy, so and aggregating the bandwidth. So essentially, you're turning two separate 100 or 1 gig links into a logical 200 megabit or 2 gig link. And we'll talk about that further as we get through this. Mohammed, do you want to give us an Ether channel modes overview?
Yeah, so let's talk about the different Ether channel modes that we have. We can start with the static, which is also known as mode on. In this mode, you just make the switch mode on. You just statically configure port channel and the both ends, they just create the port channel. Now with this, it's fast, but it's also dangerous because misconfig could lead to black holes. And if you also have to make sure both the ends they have the matching config on the interfaces as well as the port channel config as well. Better will be PAGP, which is Cisco proprietary, and it uses PDUs to exchange communication on what the different, let's say, speed the interfaces have that are joining into port channel, or the is it a layer 3 interface? Is it a layer 2 interface or a switch port? So using a dynamically setup using PAGP is much better than mode on, but it's only Cisco only, so it's Cisco proprietary. Better will be IEEE standard 802.380, which is LACP. It's an industry standard and it offers active passive mode. I mean, PAGP also has auto desirable modes where one switch can be the leader and just sends all the traffic for the communication of PAGP or the port channel establishment, and the other end can just listen and take that info and create the port channel. Both LACP and PAGP offer that the dynamic modes. And LACP also supports standby links, and it is preferred in all new designs. So PAGP is not preferred. Even if you're using Cisco equipment, you should use LACP as that is the industry standard. In the images that we have on this slide, we can see that on mode on, both the sides just say we are on. We're getting the port channel interface, the port channel virtual interface, and we're gonna have, like, let's say port 1 and 2 in that port channel. And switch 1 and 2, if all the interface configs match, the speed, the duplex, the STP settings, like we mentioned on the previous slide, it's gonna establish that port channel. But if there is something, if there is a misconfig, it's not gonna establish, and it's gonna be very hard to troubleshoot. With LACP and PAGP, you can get much more details, either through the packet capture, if you can do that, or just through the show commands that you can do on the switch. So in the picture below, you have LACP/PAGP, where one end is listening only, or I mean, in this one, you could say one end is listening, the other one is sending the traffic. As long as one end is listening, the other is sending, or if both are sending, it's gonna establish that communication, and it's gonna establish a port channel if all the configs match. So I think that's a basic overview of all the different modes.
Yeah, and you'll notice through when you onboard into a enterprise, you'll notice that ether channels are normally represented by this oval sign right here.
Yeah,
So that is a
yeah,
very common thing to see.
yeah.
Right, but moving on to the next slide. The static ether channel, some of the facts about it is absolutely no negotiation frames. We'll get into the config later, but you're essentially going into the interface and you're just turning on link aggregation. So there's no LACP frames, no PAGP frames. You're statically setting up a link aggregation port channel. So it requires careful config alignment because the ports must match. Uh, the .1q encapsulations must be the same. The MTU must be the same. The native VLAN must be the same. If not, the switch will complain about it and you'll be able to see it through the logs. Excuse me. It has the lowest overhead, however, so you won't be adding any extra frames to your data, but highest risk because, again, if you were to misconfigure one side, it could potentially bring down the other side. Um, it is very sensitive to mismatched VLANs or speed, as previously mentioned, and troubleshooting is a bit limited since PDUs don't exist, but again, these are point-to-point links, so it's not the worst thing in the world to troubleshoot. Um, but for a PHP deep dive, some of the protocol details, it is a Cisco-only negotiation protocol, so it is vendor proprietary. If you are in a multi-vendor enterprise, which most environments are in today's world, you're running Arista, Juniper, Cisco gear, you're not using PHP anywhere. And really, if you're using Cisco, if you're in a Cisco shop, really, most of the world is either on or LACP. But it sends PHP data units periodically. The multicast MAC address is represented in the slide, and the ether type is 0x0104. Some of the biggest takeaway from the slide is the PHP modes, which is auto. Essentially, you are listening for data units, but you're not sending any. So you'll be RX, no TX, or desirable, which is actively sending PDUs and saying, hey, I want to create a port channel. Hey, I want to create a port channel. Hey, I want to create a port channel. And then one side is just listening for them. If you are both desirable, they're both sending these data units and it will negotiate to a PAGP port channel. It exchanges device IDs with MAC addresses, the port number in which the interfaces are that are going to be aggregated are, the group capabilities, which is the channel group that you define, the learning and forwarding states, aggregation flags, partner device, and port ID. The timers are fast and slow, which is 1 second to 30 seconds. The negotiation process. So the device in Desirable sends a data unit. The remote listens, whether it's auto or desirable. They both compare system and device IDs and group abilities and port consistency. If it all that matches, it is compatible and joins in a port channel is created. If it mismatches, the member is suspended, and you'll be able to see that through the show interface commands. Failure detection are missing PDUs, channel down, mismatch VLAN, suspended member, and if there's a speed or duplex mismatch, say on switch A you have a 100 megabit link and on switch B you have a 1 gig link, you're not going to get a total of 1 gig plus 100 megs. Now you're just going to, it's going to fail and it's going to say no aggregation. Um, Mohammed, do you want to give us the LACP deep dive?
Yeah, so LACP, you got the protocol details. So it's a standard, it's an industry standard. IEEE 802.380 is where you will find the specifications on LACP. It uses LACP DU frames. Ether type for LACP frames will be 0x8809. The subtype will be 0x01. The multicast MAC address is shown on the slide. The LACP modes, again, the most important part from the slide is active and passive. In PAGP, in desirable mode, the switch will send the traffic, and if it's auto, the switch will listen. Same in LSCP. In active, the switch will send the LSCP to use frames, and then in passive, it will just listen for those LSCP. So the neighbor or the peer will be sending the LSCP to use. Now the fast timer is 1 second, and slow timer is 30 seconds. Can I go to the next slide?
Yep.
Okay. Um, this slide has a lot, but if you actually read through it, it will make sense. So this is what a LSCPDU frame will look like. From the top, you have your destination address, source address. You got some of your subtype and type that we mentioned on the previous slide. Till you get to the TLV type, and here it says Carlos, can you go to the TLV type where it says?
Yep.
Yeah, let's go through this. So here you will see the different fields that the LSCPDU has. In here, you will see the actor information. The actor information is the device that is sending the LSCPDUs. So that device is going to share its system priority. It's going to share the system ID, which is going to be MAC address, the key, the port priority, and then it's also going to send the port number and the state bits. It's going to also include the partner information as well. And this partner information will, of course, will be received by the device and will have that information. So here it will be identical structure as the actor information. So you will have all the information that the actor has, but also for the partner in the same LSCPDU. The LSCPDU will also have the collector TLV information, and that information is used for coordinating or forwarding/collecting. And then you also have terminator TLV, which is all zeros and it ends the TLV chain. By the way, TLV stands for type length value, and it's essentially for explaining, system priority, what the value it has, what the length of that uh, the sequence is. Can you go back to the other one, the other
Yeah.
slide? Yeah. So now that I explained that, it will make sense. As you see the actor information, the actor system priority, which has 2 octets, the actor system MAC address, you will see actor key, then you have some reserved, then you go to the TLV type, partner information, and that's where you see your peers information. So you'll see the partner information, you got the partner system priority, you got all that information, and then you got the collector information and then the termination. So that's how a LSCPDU frame will look like. And it includes pretty much like your system's information for the port channel. And it includes the information from the peer on how how the config looks like over there. So if there's a mismatch, it will see here and it will be like, okay, we cannot establish the port channel. Now we can go to the next slide.
Yeah.
Okay. So these are some of the bit level state flags. What these state flags are used for is essentially to tell the other peer on what the LSCPDU or the LSAP config is on that device. So the bit A is used for the activity. So is the switch actively doing the LSCP, or is it passive, or is it just listening? The B is for the timeout. Is it doing short timeout or long timeout? C is for the aggregation, and so on. So these bit level state flags, these are essentially used for your LSCP config on, if you're doing active or passive, etc. And why these bits matter is because they control the forwarding permissions and synchronization. So no traffic flows until collecting and distributing are both on. So in this one, in these bit state flags, you will see E and F. Those both flags have to be on for LSCP to work. Can you go to the next slide?
Yeah. No, thank
Okay.
you. And yeah, there's a lot of granularity that goes into
Yeah.
LACP, and it is very customizable. But depending on the environment, a lot of folks just turn active and aggregate. But
Yeah.
one of the things I have seen though with when talking about this slide, load balancing. So whether you're doing statically PAGP or LACP, the point of having two links is that you're balancing across two links. You're aggregating the bandwidth, so you're turning a 1 gig, two independent 1 gig links into a 2 gig pipe, which you
Hmm.
got to load balance across those physical pipes, right? That 1 gig, you're going to send certain traffic across, A side of the port channel and B side of the port channel. So there are some hash inputs. Essentially, how are you going to be load balancing? Is it based on source MAC address? Is it going to be on destination MAC address, source IP, destination IP, TCP and UDP ports, and layer 2 and layer 3, or even 4 combinations? An important note is one flow always maps to one physical link. So multiple flows equals true load balance distribution. Um, Interestingly enough, when I first started my career and I was working in a data center environment, we had a client who we had an LACP set up for, and these were two 10 gig pipes. However, they were noticing a lot of packet loss across this port channel, and when we took a deeper look into the SNMP data that was available to us at the time, we noticed that packets were being dropped because it was not load balancing correctly. So they were sending
Oh.
all traffic to it was basically load balancing based on destination IP, and they were doing
Mm-hmm.
some SFTP transfers to the cloud. So it did not load balance across it correctly. So across one 10 gig pipe, they were bursting all the way up to 10 and dropping packets, and then the other pipe basically remained unused. So as a workaround that, we ended up actually load balance based on destination MAC address because on side B, you have also on side B, uh, we had two separate ports that the destination MAC address would actually change, right? Because one is the next switch, the other one is the next switch. So it would load balance perfectly across them. And basically, my point with this is
Yeah.
that do not do not overlook your load balancing protocols.
Yeah. Yeah.
Yeah. But basically, the last part I want to get into is the static LACP and PAGP comparisons. Um, Essentially, what is going to negotiate a port channel? Active will negotiate. Active passive will negotiate because you have a TX and an RX. However, active and desirable are, you're getting into an LACP and PHP, so that's not going to negotiate. And on, you have to statically configure. So active passive will negotiate. Passive passive, nobody's ending any LACP PDUs, so it will not negotiate. And then same thing applies here. This is LACP and PHP protocols, so that will never uh, negotiate. With PHP, desirable and auto, if your link B or side B is running LACP and you're doing PHP, you're never going to negotiate. However, if you have desirable, you will. Same thing with desirable and auto, because you are getting that TX and RX. Auto and desirable will. Auto and auto will not, because you're not getting any PHP PDUs. Um, Again, with static, it's just on. There's no other mode
Mm-hmm.
you can enable. But that pretty much is the conclusion of our slides. There's a lot of information there, a lot of it which, like most things, you do not use in the real world, but it's good to be aware of because you never know when they can come up.
Mm-hmm.
But if we want to get into the lab aspect that Mohammed and I have prepared for this, uh, let me go ahead and share it. So this is the lab that Mohammed and I have set up for you guys. This is a very simple um, three-floor enterprise with three-floor switches and a core switch, which is doing the routing for us. On the left side here, you'll see that we have a VLAN 10 computer and a VLAN 10 computer on the first floor. So what we would like to show is a link failure happening and how that does not affect the network because of the redundancy that the port channel has created for us. So getting into the configs of it, here we have our computer, which is the one on the third floor. It is 10.10.10/24. On floor 3, we have a VLAN created, which is VLAN 10 for users, and have assigned our VLAN 10 PC to it. And I have preemptively configured a port channel, which I'll go over the configs right now. So if I do show run int FA01, oh, I don't think it likes that command because
Yeah, it
of
does not like it.
yeah, the switch, right?
Yeah.
And also our environment. My virtual environment was not working for this video, but we'll be back with that for the next video. So if we do FA01, so FA01, you'll see here this command. So FA01 and FA02, I have created channel group mode on, which I'm statically saying you are going to be part of a link aggregation group. And then what I've done, actually, you'll notice that this trunk configuration here has been trickled down to the interface configuration, but it's actually configured on the channel group interface. So if I am able to find it here, the interface port channel 1, which I created with the channel group 1 command, that's where I actually go in and configure it. The same applies here. So if I do show VLAN brief, this is the core switch side. You'll see that I don't have any switch ports as assigned to it. However, if I do show interface trunk, you'll see that PO1 is encapsulating that VLAN. And if I do show run in VLAN 10, oh, I don't think it likes that either. You'll see as well the same applies with FA05 and FA06 and VLAN 10 configuration here. Okay, so let's get on to the next portion of this, where we continue this. I am going to go ahead and assign an IP address to this computer now, which is 10.10.10.20/24. And let me see the configurations here. Show from int fade up. So you'll see that so far I have only configured the drop link into the computer, and FA01 and FA02 are untouched. So we're going to start off this configuration. We know that our physical links are Fast Ethernet 1 and Fast Ethernet 2, which are both 100 megabit links. So if I do show int FA01, you'll see it is a full duplex 100, and FA02 is a full duplex 100. So I'm going to go into configuration mode and do interface FA01, interface range FA01, and FA02. So in here, I'm going to enable a PO interface and tie my physical interface back to this logical PO interface. So I'm going to channel group 1, mode on, and you'll see that changes the state to up. And then I will go into the actual logical interface and define my trunk configurations. So this will be a switch port, switch port mode trunk, switch port trunk allowed VLAN 10. Okay. And then on the other side here of the core switch, I'll have to go ahead and do the same. You'll see that it is complaining about Fast Ethernet 1 and 2 because of the port type, because it's not matching what is on the other side. So what I'll do is, now we got to make it match. So I'll go in and say config t and FA01, or sorry, interface range FA01, FA02, channel group 2 mode on. Now the channel groups do not have to match. You'll see here that it is complaining about the VLAN not being the same. So we'll go in to the PO2 and do switch port trunk allowed VLAN 10. Okay. Switch port trunk encapsulation .1q. Okay. So now let's see, show run. And if you look at the PO1, it now has the configurations that matches floor 1 switch side. It is PO2. Oh, and I actually forgot in PO2 config t, PO2 switch port mode trunk. And there we go. So the port consistency has been restored. So if I do show run again, you'll see that our configuration now matches for PO1, which is that port channel down to floor 3, and PO2, which is that port channel to floor 1. if I do the show ether channel summary command, you'll see here that it is FA05 and 6, which go to floor 3, are part of PO1, and FA01 and 2, which go to P2, are both in use and being leveraged. So some of the interesting commands is this show ether channel summary command, which tells us what our port channel groups are. You could also go into details more if you just remove the summary. Here we'll see that group 1, the group state is layer 2. The maximum amount of ports supported in a port channel are 8. That's the limit of what you can aggregate. So the most we could have here is an 800 megabyte port or megabyte logical interface. So here, now if we do, or megabit, sorry.
Yep.
So then if I do show VLAN brief, you'll see that again, we do not have anything assigned, but in theory, I should be able to ping now all the way to that other computer. So
Yeah.
if we go here, can I ping my gateway still? Yep. So I can ping my other computer. Okay, great. So we have data flowing through these port channels. And if I create a consistent ping here, if I create a consistent ping here, oh, can I do not do -T to keep that going?
I'm not sure if packet tracer does that. You might need to do the question mark, see what it shows.
I didn't do anything. Okay, so
ping and question mark.
Yeah, okay. So it only likes that, but that's fine. We can still simulate a link failure. So if we are FA01 in this case, and let's assume our FA01 link is going to go ahead and just get disconnected. Let me see. Mohammed, do you remember?
Yeah, you had to click that. You had to click that. You're at the right place. You're at the right place at the top. That back thing. You click on that. Now you'll be able to do it.
Perfect. Okay.
Yeah, it does that sometimes.
Okay. So if we simulate a link failure here, okay. Well, actually, before I do that, I want to get into what the bandwidth looks like now for this.
You have to click on the thing again. At the most left in that. Yeah.
Interesting. Okay. Sorry, everyone. Okay. So if I do show interface PO1, you'll see here that Packet Tracer is actually lying to us because it says it is a full duplex 100 megabit per second interface. However, this is actually now a 200 megabit per second aggregated interface. You'll see here how the bandwidth is actually 200 megabits, but it's not being reflected here. I think this may be a bug within Packet Tracer, but I know in the real world it will
the bandwidth
show you
should
the
be
aggregate
200
bandwidth.
megabits per second now. Yeah.
Correct. Yep. So if we just wanted to point that out, that you'll see what the aggregated total is in the PO configuration, and you'll see the output packets and input packets here, which ties in your physical. So you can still go into the physical ones. So if I do FA05 in this case, FA05, you'll see that the numbers will be different. You'll see here that we have a 956 packet input. However, here we have 956 packet input. Yeah. Oh, you know what? It's the load balancing mechanism that's in play.
Okay.
Because
Yeah, I think it's saying destination IP then.
Yeah. Well, let me see. Let me see. Let me.
I need to find the command.
Yep. I don't know if it'll like it. Show ether channel load balance. There you go.
Oh, it does like it.
Yeah, it does like it.
Oh, it's doing source MAC errors.
Yep.
Oh.
So because of that.
Okay.
But
yeah, that makes sense.
In a big enterprise where you have different MAC addresses, then you will actually be then you will actually see different rates at different physical interfaces.
Okay.
But that's why.
That makes sense. Yeah.
It's for the sake of the lab, obviously we're not able to replicate everything. Um,
Yeah.
but the logical idea is there. So if we go now to simulate the link failure, right? We have our computer which is able to ping here with no problem. Okay, it's still able to ping. And if I delete, it's up. If I delete this link here and I try again, we see that it still works. Although we
Yeah.
had a physical failure across the path, we are still able to talk, and our switch redundancy is degraded, and our bandwidth is degraded in theory, but we are still able to have communication as opposed to a full failure if we only had a single link. What this does is we'll see here that the switch logged that failure. So Fast Ethernet
Mm-hmm.
5 went down. So if we do show Ether channel summary again, you'll see that there was a D down. 405 went
Yeah.
down. However, the PO is still in use. The PO is still transversing traffic. So our ping is still able to work, and the same applies if this link were to die here. If this link were to die here, we
Be
should
able to ping.
experience
Yeah.
a degradation of service as far as redundancy goes, but our
Mm-hmm.
ping will still work, and we are able to create that redundancy. Now, how does this apply to the real world? There are critical services, and here, we're talking about 100 meg, 200 megs, which is not real world bandwidth anymore. But
Mm-hmm.
when we're talking now about this being 10 gig pipes or 100 gig pipes,
Yeah.
you're still able to forward traffic in the event of a physical failure.
Yeah.
And this is not limited to a floor switch. This is limited to data centers. You can have
Yes. Yeah.
AEs across data centers. You can have AEs, also aggregated Ethernets, which you will hear that term for the port channels. You can have port channels across data centers. You can have port channels across buildings. Um, so it is very much leveraged in real world. There are other topologies such as VPCs that Nexus are doing, or MLAGs with Aristas, that are kind of like port channels, but on steroids, I'll say, because now you can talk to individual devices. But this is the technology that is still very much used today and very good.
Mm-hmm.
You,
I
you,
agree.
we could have done this lab with LICP or PAGP. The same logic applies. The configuration is very minimal in difference. Um, and that's all I have. Mohammed,
Yeah. I
anything?
think I think we covered the gist of it. Uh, what Ether channels or port channels provide is like redundancy,
Yeah.
but also more bandwidth. So it's
Yep.
like best of both worlds. And
Yep.
also STP. You don't have to worry about STP now because
Yeah.
it shows as a one logical link
Yeah.
to STP and it doesn't mess around with it. So I
Correct.
think we covered
It doesn't,
pretty
it does
much
not
completely.
create a loop-free environment, because if you
Yeah.
are connecting one switch back to another switch and creating that triangle, which we talk about with spanning tree, you're still going to create a loop. You're still going to
Yeah.
have downtime, but it does eliminate that blocking port as far as um, it does
Yeah.
it does eliminate that blocking port as far as aggregation goes and
Yeah.
redundancy
Exactly.
goes.
Yeah.
Hmm.
Yep.
Okay.
So I think we covered everything. Yeah, I mean the LSCP and PHP config is pretty much the same. You just
Yeah.
put the mode for LSCP or PHP. So
Yep.
that's pretty much it. Yeah.
Okay. That sounds good. Well, thank you, Mohammed, for joining
Yep.
me
Thank
tonight,
you.
and we'll be in touch with another video.
With another video
All right.
soon, hopefully.
All
Thank
right.
you.
Sounds good.